This is Ms. White. We are beginning our bonding unit, and this video will be about types of bonds. Remember that atoms seldom exist as independent particles in nature, and nearly all substances consist of combinations of atoms that are held together by chemical bonds. So a chemical bond is a mutual electrical attraction between the nuclei and the valence electrons of different atoms that binds those atoms together. So how electrons interact will define the type of bond. A bond is an intramolecular force, which is an attractive force within a molecule or a formula unit. Remember also that atoms bond to reduce their potential energy and to increase their stability. We are going to look at 3 types of bonds: ionic bonds, covalent bonds, and metallic bonds. In ionic bonding, a cation loses electrons and an anion gains electrons. We've talked about that before. There is a complete transfer of electrons. The resulting compound has no charge and is neutral, and the ions are held together by very strong electrostatic forces between the oppositely charged ions. It can require up to 4,000 kilojoules of energy to break an ionic bond. Remember that the fundamental particle of ionic compounds is the formula unit. Let's look at some properties of ionic compounds. Most are solids at room temperature. In an ionic compound, the ions combine in a crystal lattice structure, and you can see it over here. And it has a repeating geometric 3D configuration. There are forces of attractions that hold the ions together in that crystal, and that makes it difficult for one layer to move relative to another. So these layers do not move with respect to each other. This makes ionic compounds hard and brittle. Ionic compounds also have high melting and boiling points. Many ionic compounds are hygroscopic. What that means is they absorb water from the air, forming hydrates. We have talked about hydrates before. A few are even deliquescent, which means that they actually dissolve in the water that they absorb and end up forming a solution, which we can see here. Most ionic compounds are soluble in water. Ionic compounds can be electrolytes. They can conduct electricity either in the molten state, which means when they are a liquid, or when they are dissolved in water, but not in the solid form. In order to conduct electricity, there has to be free movement of charged particles, ions in other words. In the solid state, the ions cannot move. Remember, they are in that rigid crystal, so ionic compounds cannot be electrical conductors when solid. In the molten or liquid state, ionic compounds can be electrical conductors because now the ions can move freely to carry that electric current. When they dissolve, their ions separate from each other and become surrounded by water molecules. Now the ions are free to move throughout the solutions, so they become electrical conductors. And over here, we can see the ions moving around in the water, and they can light a bulb up, meaning that they are conducting electricity. Now let's look at covalent bonding. The atoms involved are usually nonmetals and metalloids. Electrons are shared in covalent bonds, and the fundamental particle is the molecule. In a covalent compound, the bonds between the atoms are strong, but not as strong as for ionic bonds, and up to about 1100 kilojoules of energy could be required to break a covalent bond. Also, the forces of attraction between the molecules, which means over here, in between molecules, are much weaker than the forces within formula units in ionic compounds. So in a sample of a pure covalent substance, the different molecules are held together by weak intermolecular forces, or IMFs. The difference in the strength of attraction between the basic units of covalent and ionic compounds will give rise to fairly different properties in the 2 types of compounds. Let's look at some common properties of covalent compounds. They can be solids, liquids, or gases at room temperature, so all 3 states of matter, but most are liquid or gas. Some examples: for solid, glucose and wax; for liquid, ethanol and bromine; for gas, carbon dioxide and hydrogen. Polar covalent compounds are soluble in water, and non-polar covalent compounds are insoluble in water. For now, we will stick to that. We will learn more about why that is later. Covalent compounds also have lower melting and boiling points in comparison to ionic compounds. They vaporize easily at room temperature, which means they go into the gas phase, so you can smell them. That's why some air fresheners are made from covalent compounds. And this is due to the weak intermolecular forces that hold the covalent molecules together. Covalent compounds in their original state of matter do not conduct an electric current. This is because a neutral molecule cannot carry an electrical charge. Also, most covalent compounds, when they dissolve in water, they will retain those molecular structures, so they will be non-electrolytes, which means they cannot conduct electricity because, again, neutral molecules cannot carry an electrical charge through the solution. If you see the pictures, here we have an ionic compound which dissolves in water, forming those ions, which can carry electrical charges. In a covalent compound, we retain the molecules. There are no charges, so no electric current can be conducted. And we can see over here that the light bulbs do not come on if we have a covalent compound, but with an ionic compound, the light bulb comes on. Finally, let's look at metallic bonding. The forces of attraction that results from the attraction between the cations of metal atoms and their surrounding valence electrons is metallic bonding. The valence electrons are delocalized and they travel freely through the metal sample. So that forms a sea of valence electrons which are moving freely in between the metal cations and core electrons. Those positive metal cations are then attracted to the negatively charged electron-rich region between the atoms, and that forms metallic bonding. Metallic bonding is not actually a real bond, and the fundamental particle is the unit cell. Some metal properties: all metals except mercury are solids at room temperature. They are also packed in a crystal lattice, similar to ionic compounds. The closely packed atoms with mobile electrons make it that metals are great electrical and thermal or heat conductors. Some more properties of metals. The crystal lattice structure and strong forces of attraction make them hard like ionic compounds. But because metal atoms can slide across each other, unlike ionic compounds, they are not brittle. They do not break apart easily. Metals are ductile, which means that they can be drawn into wires. They are malleable, which means that they can be hammered into shapes. They have high melting and boiling points, and they have luster, which means they are shiny, and they are opaque, which means that you cannot see through them. Metal alloys are a mixture of two or more metallic elements. Most metals that we use are actually alloys. They contain the same type of metallic bonding as single metals. Some examples would be brass, which is copper and zinc, 14-karat gold, a mixture of gold and silver, bronze, copper and tin, and there are many more. This concludes our Bonding 1 video, bond types. You should have taken high quality notes, rewatch the video as needed, and ask your questions in class.